Okay, I think we can get started. So, hello everyone. Today we have here Bruna presenting her latest paper on archive. I will keep an eye on questions. So Bruna told me that if you want to make questions during the presentations, please do just raise your hand, and I will tell Bruna that we have questions. Yeah, otherwise I think that's it. So the screen is yours, Bruna.
Okay, thank you. Can you guys see okay?
Yep.
All right. So today I'm gonna present, can one distinguish Caroli-de Gennes-Matricon and Majorana states in vortices, which is our latest archive, or because Antonio is also involved, and I'll talk about our collaborators later. And just to outline, we're gonna contextualize a bit the vortices and those two states, what they are and how they appear. We're gonna talk about zero bias peak in experiments. We're gonna explain what is our system, how detrimental are the impurities, and some conclusions. Okay. So a way to contextualize this is to talk about topological quantum computation, which means working with non-abelianians to try to create a two-level system with braiding that's going to translate the logical gates in quantum computation can be done via braiding, and you're going to have quantum computation that is robust against local perturbations, which is pretty interesting. And I believe it's the only quantum computation setup that can do this. So that's promising. And a possibility is to work with Majorana bound states. And here I'm mentioning two important characteristics of Majorana bound states, which is the zero energy mode that is robust due to topological feature, and the zero charge that comes from particle-hole symmetry of the system. And I also want to mention here that we have different platforms for Majorana bound states, for instance, nanowires, which is widely studied in vortices, fractional quantum halls, some other platforms, but here we're focusing on 2D, on vortices. And just so to emphasize this, we have those two characteristics, the robust zero energy modes, which implies in zero bias peak in conductance, and the zero charge. So due to this, the observation of the Majorana states, they tend to rely on zero bias peak. And here are some experiments they can show that I can mention that involve vortices. So it's very common to see this kind of plot that you have a conductance, zero bias conductance map, kind of a real space way to see that you have a peak here in the center of the vortex. He is kind of the same intensity plot looking at this line here. And those types of waterfall like plots with different energies, the spectra in different energies, and you should see that the one in black here, which is the one on the center of the vortex, is one that have a more intense peak of bias, peak of conductance for zero energy, right? Here's another way to see, just with some selected values of those spectra, right? That's a paper in Science. Another paper that has similar plots, but I decided to put another plot that is a bit different, but also emphasize the zero bias aspect of it. And here they use, I forgot to put here, but they use different values of magnetic field from lower to higher. I believe it's 1 Tesla, 2, and goes to 6 Tesla, and you see the bias going down. So that's a very prominent feature. a third one here that I think is interesting to mention, because this one says that is impurity assisted. So you have similar plots, real space plots, the waterfall like, and it's interesting to see the presence of impurity. We're gonna talk more about this. So what else besides zero bias peaks? In this sense, we look at a paper, the archive preprint, that mentions the use of non-local transport in vortices, which non-local transport, particularly in vortices, that they use STS to manage to find information about charge in a non-local way. So that's why I'm emphasizing charge so much, because that's a proposal that also involves the take a look at the difference between charge, the spectre zero energy, the spectre zero charge that you have for Majoranas in comparison to other states. So this is a bit of context what we have in the experiment so far. Is a question?
Yeah, there's a question in the chat. So the question is, why is the Majorana zero mode appearing at the center of the vortex instead of the edge of the vortex?
Well, it appears at the center. There are some, I believe there are some periodic boundary conditions that explain why the zero energy, the Majorana appears at the center. But what you expect is that you have the Majorana in the center and another one in the edge of your whole system, kind of enough far away. So we consider just the one with in the center of the vortex. So the point here that we have to pay attention is that we have other states in the vortices, such as Yeshiva-Husinov, which we're not going to talk in this situation, because we're going to focus on Caroli-de Gennes-Matricon, which are, both of those are trivial, they are not topological, but in particularly, it's interesting to know that Caroli-de Gennes-Matricon, they have a spectrum that's something like this, energy proportional to an M, which is integers that start with 1. And it's proportional to delta square over mu. Let's see, another question. Okay. So can one distinguish Caroli-de Gennes-Matricon in particular, and Majorana stays in vortices? And that's our whole issue here. So to study this, we're gonna first characterize our system. We're gonna think about two systems to compare. Both of them would be 2D electron gas plus S-wave superconductivity, trivial S-wave superconductivity, in the sense that we're not adding any other components to make something like something that would mimic P-wave and be topological. We're not adding spin orbit or Zeeman. So S-wave here, trivial, and P-wave. So we have a trivial and a non-trivial when you're considering a clean system. So just to show, this is, sorry for the low resolution, but that's what will be the other parameter, delta. It has sort of a hyperbolic tangent aspect, so it's 0 inside what would be the vortex, and some constant value delta 0 outside, and it's a bit smooth here. And this value here, psi, it characterizes the size of the vortex. We avoid putting equations, so I'll just explain this qualitatively. And phi is the phase that you have in the superconducting outer parameter. So just to summarize what I mentioned here, S-wave versus P-wave in a clean system, you have here for S-wave a spectrum that doesn't have a zero energy state, starts above 0. And here, P-wave, you have a zero energy state and the other states, but the important thing to notice is the zero energy state, which is robust. It doesn't go outside, doesn't change, doesn't move from zero, right? That's the Majorana that we expect. Also, there's the charge. Here are the values of the charge. As you can see, you have difference in the charge here, and here should be neutral, right? As we expected. So robust zero energy and also charge neutral. That's for a clean system. So is the spectrum enough to differentiate the states? And here we explain that not really. I don't know why it's so low res here, but here is just a way to visualize what we want to say here. We have in P waves something like a quantum of physics with zero energy here. There's a Majorana and equally spaced levels. And in S wave, this red energy would be the clean S wave. But what we're claiming, what we're going to show is that with some impurity, we may be able to shift down those energy states to get arbitrarily close to zero for this lowest energy CdGM state. So some wisdom from the nanowires, just to contextualize that that's not a brand new idea, because you have from nanowire physics, you have a paper from Penn and Sarma, when they characterized three different types of zero bias peak that might appear. One is the good, the bad, and the ugly. So good will be a pristine material, and then we can claim that the zero bias peak is indeed topological. The bad one would be a zero bias peak that comes from quantum dot effects or homogeneous chemical potential, which is what we're gonna talk about later. So it's actually a trivial Andreev type of state, Caroli-de Gennes. And ugly, which is strong disorder. And here from the same paper, just to show, this is a type of bad zero bias peak. So you have the pinned zero energy state, but coming from effects that would be related to the bad regime. So for our vortex thing, we're thinking about adding an impurity and see what happens, right? So in this case, we add a screen charge impurity for our S wave, again, the trivial system. So it's going to be a term like this. Delta mu is the potential strength of this impurity. Eta is going to be the screening length, and you have a Gaussian type of impurity, scalar impurity. And now we see that we have a different spectrum here. So S wave with impurity, now they're both S wave, we're just plotting different things, eta and delta mu. And now we can see that the states, lower energy, they go as close to zero as you want. And also at the same time, the charge goes to zero. So they both go to zero at the same time. And that's an issue because that's what we're thinking that it should be able to distinguish a trivial and non-trivial state so far. Okay, but is this a sweet spot of the system? Maybe we're just tweaking the parameters in a very specific way. And now here, to test this, we show for a different set, a larger set of parameters, both energy and charge for delta mu, eta, and psi. And we see that the suppression of both energy and charge happens in quite in big regions of the parameter space, in any parameter space. So it holds beyond the highly localized regime, this one. And also we can see that these suppressions for both energy and charge, they go together. We don't have many situations when you have just the suppression of one and not the other, right? So going back to the original question that we had, can one distinguish Caroli-de Gennes-Matricon and Majorana states and vortices after all? And here, just to show those that they might be the same picture here. This picture is on our archive. You can see better, but here we're using Green's function just to show the density of states here in red and, sorry, the density of states in black and the charge in red, and you can see that they look very, very similar. So, and before thanking everyone, I want to thank my collaborators, Antonio, the host here, Luis Gregorio, who's my advisor back in Brazil, University of São Paulo, and Nancy Sandler. She was my advisor when I spent some time on University of Copenhagen. So that's it. Thank you all. And here's the manuscript if anyone wants to check.
All right, thanks, Bruna. Do we have any questions? Anton has a question. You can just unmute yourself.
Yeah, so a quick question. I find it remarkable that the mode is that the Caroli state is so close to the zero energy. Do you understand why? Like under, or more specifically, like, is the parameter range in which the Caroli states are so close to zero energy, is it like a broad parameter window or is it narrow? Do you know how universal is the effect?
Yeah, we try to characterize here, thinking about this. We actually had a larger plot at here went to until 20, and we see this suppression happens for larger values. So it's beyond the highly localized regimes. We test different values of the impurity, at least of the impurity we test, which is characterized by the delta mu and the dieta.
And is there can one make some kind of analytic argument or to understand which features of the model result in this behavior?
Yeah, I believe this should show analytically because actually this plot comes from, yeah. The component here is this one, right? So I believe if you go analytically and diagonalize, you should see the difference in the energy appearing anyway. There's also expression for the charge, for the Caroli-de Gennes that we don't show, but you can show that Caroli-de Gennes charge is always different than zero, above or below. And I believe you can do the same analysis and see that this charge is gonna collapse.
All right, thanks.
Any other questions? Yeah, Elsa.
Hi, everybody. So I just wanted to ask Mohammad to elaborate a little bit more on the question he asked in the chat. So I think he was referring within the vortex itself where the wave functions should be localized. And there's been some other messages in the chat, but maybe he wants to comment for everybody.
Does someone wants to comment about it or?
Well, I was saying Mohammad since he
okay.
Since he mentioned it. Maybe he doesn't want.
Hi, thank you for your presentation. My question was about the fact that, you know, I was thinking that is zero mode energy should somehow exponentially be localized at the interface between the topologically trivial and non-trivial region. But when you see this experimental observation, the zero mode is always appear at the center of the vortex, and that's my question.
So you're asking if there's possibility for it to appear somehow dislocated from the center of the vortex.
Exactly, yes.
Well, I think it can be a bit homogeneous. Like here, you can see that it should be in the red regions, kind of homogeneous, and I believe that should be effect of your substrate.
I think this has to do with the proximity effect, let's say within the vortex. So if the gap penetrates really until the, let's say, the center, like going down this way, I would say it tends to be localized just at the very center of the vortex, whereas if the gap decays somehow faster towards the center of the radius, it might be expanded, no? In principle, that's what I would, if one considers that, let's say, the chemical potential all across the vortex is constant.
All right, thank you.
Yeah, I mean, the format, analytical format is something like hyperbolic tangent, right? So it should be characterized, the delta mu, the delta naught here should affect the psi should affect. But I think it makes sense to think that it should be homogeneities. That's why I think it's an important thing to consider. It does appear.
I was, well, if nobody asks anything else. So, because, sorry, before I was checking the chat and I couldn't really listen to the answer to Akhmerov. So in principle, the energy of the Carolis could be arbitrarily close to zero, no? That's what you just concluded?
Yeah.
Okay.
We conclude, yeah, we conclude from, sorry, this plot, right? You can see from, especially the delta.
I mean, even in the absence of impurities. Or
no, this one is this one's with impurities. Yes.
And in the absence?
The absence.
There is some kind of minimum energy for the Carolis? Yeah,
or we're considering here S wave pure. So we should see only Caroli-de Gennes, this kind of a spectrum, the m delta square over mu. So it's the one on the left. No zero energy, very clear distinction of the charges. That's the one with clean, with a clean system, both S and P wave. And here in this other plot, both here are S wave. We're just plotting psi and delta mu. And you can see that it goes to zero, arbitrarily close to zero. Yeah, both energy and charge.
So, okay. So in the clean case, it depends on the coherence length you showed, and what else?
In the clean case?
In the clean case, yes. The starting point, let's say.
Yeah, the clean case, the
energy of the
case. Yes, should depend on those. Because the system here is just the to the electron gas, so only this and S wave term. So there's not much to depend on. We did the simplest possible, just these two terms. So there's no where else to blame the those effects, right?
Okay, thank you.
I think Victor has a question.
Yes. Hi. Can you hear me?
Yes.
Okay. I am just trying to see, because I'm wondering what is the other Majorana, right? Because I'm just trying to picture it within the Rajba nanowires, right? So for a finite Rajba nanowire, so the Majoranas are located at the edges, right? But then here, so it's one Majorana located in the vortex core in the center, and the other is not localized, or where is this second Majorana?
It should be in the edge of the system. No, not the edge of the vortex, but you predict it to be an edge state of the system. And also it depends on other things like how many Majoranas you have in the system, depending if it's an even or odd number. It might become an edge state or might become everything in pairs inside the vertices.
Right. Okay. So it's not localized. Okay.
Yeah. And for computational point of view, we can think that we're just excluding those. We're just considering states inside the vortex. We can compute only the states inside the vortex, which is what we did here.
Okay. Okay, thanks.
Matt has a question.
Can you hear me?
Yes.
Okay, thank you so much for the presentation. I was going to ask about the S-wave part. So, I mean, what would change if you include, I don't know, for the 2-deck, a Rashba spin-orbit coupling and maybe a magnetic field to mimic the bound states around the vortex? So would that, I mean, would your conclusions change in that case?
So if we add both spin orbit and Zeeman, you should have something that is sort of a P-wave. They have those setups for vortices that they say that they are heterostructures. So you have S-wave that should be trivial, but you add both Hashba and Zeeman, and you can see by diagonalizing, you can see that you can have Majoranas. So I believe it would complicate things from the standpoint of evaluating our results, because we could add those terms, but the idea of using only S-wave in a 2D electron gas is to make sure that we're thinking only about something that is necessarily trivial. S-wave with 2D electron gas should be trivial if you don't add any components. So we can say, oh, we're only studying Caroli-de Gennes.
Okay, thank you so much.
Are there any other questions?
There is one in the chat.
Yeah, so Jianfeng asks, well, first ask if charge and conductance can distinguish between Majoranas and trivial states. Can braiding do it? And then after some time, I also added, so take a step back, does it mean that there's no electrical measurements, not even any non-local one that can distinguish between them?
Okay, so here, conductance and charge, the point that we're trying to make is that even if you combine conductance and charge, conductance with the zero bias peak and charge with the non-local measurement, or however you want, can be deceiving, right? About braiding, that's a more complicated issue because you have something like the quasi-Majoranas, which I don't think it's our case, but you can have something that it's not Majorana that can braid in a non-trivial way. So probably not even braiding, I don't know. But there's a thing to explore, right? To see if those states could act sort of like a quasi-Majorana type of thing. It has a completely different nature, but if it would braid as well. And so it will be interesting because if you braid in a non-trivial way, as if it was a non-abelian, you can make topological quantification in the sense that you can have gates, but it wouldn't be topologically protected because they are not actually topological states. So I don't quite know. I don't know if there's a way to differentiate from those that you mentioned.
Well, there's one more question here from Junk Feng. So do you have any reference for non-trivial braiding of quasi-Majoranas?
Yeah, that's... I just talked about this paper. Do you remember, Antonio? I just talked to you.
So
today.
there are a few papers out, I guess. Most of them actually discuss one or two things about braiding. But there's this one from Anton, I guess. There's some discussion, also one from Cosmo, if I remember correctly. Don't have the reference on the top of my head now.
Yeah. Maybe you can send later, but there's one that is explaining the situation. That's one thing that we are starting to brainstorm about it. But we're also confused.
Yeah, so I don't see any other questions. Last chance, if you still have a question, just unmute yourself. All right, so I guess we can end it here. Thank you everyone for joining. And see you around.
Thank you everyone. Sorry for the fast presentation.